That doesn't look so good, right? Rather scary? Well, anyway. Check embryonic development where anterior and posterior axes of the segment are pointed out within the arrows. So what is segmentation? Segmentation is a feature of development stages of all vertebrate species. It gives rise to the segmented body axis, which is the most clearly visible in formation of skeleton. And this is a periodic process where embryos form a little segment that will give rise to the bones of skeleton. And this structure formed within a periodicity depending on species specific. For example, chicken form parasegment every 90 minutes and mouse form parasegment every 120 minutes.
And they form by budding off a tissue which is called the unsegmented pre-Semitic mesoderm, and it's this structure that becomes segmented with this periodicity. And that periodicity, we think, is regulated by a molecular oscillator that we call the segmentation clock that acts within the cells of the unsegmented pre-Semitic mesoderm. This can be visualized through dynamic gene expression of so-called clock genes that are expressed in that unsegmented tissue.
And so segmentation form in wild animal in step 1, degradation of an NICD protein from clock gene. So this results another NICD protein is to be activated to bind to the promoter of clock gene. Transcription and development on until the negative regulatory protein has 7 binds to the promoter of clock gene, and this results NICD is to be degraded. Outcome, promoter of the clock gene turned off, and so oscillation delays. When second has 7 protein binds to the promoter of clock gene, and this results the first S7 protein is to be degraded. In the periodicity, promoter of the clock gene is still off, and so oscillation delays until another NICD protein is to be bind to the promoter of clock gene, so can activate pathway of oscillation. Advancement of segmentation following in that manner within the wild-type animal. Step 1 to 4 circulate in that fashion. During the experimental study, when Dr. Dell and teams exposure to inhibitors enzymes to the clock gene, such as roscovitin, ZIF939, or DRB throughout the development stages of the embryos. As a result, those enzymes are increasing the stability and the level of NICD, and so NICD occupies the promoter of clock gene for a longer period than in wild-type animal, means prolonged oscillation period in embryos.
Period of oscillations determines the periodicity of somite formation. But there's an interaction between the periodicity of the oscillations and the rate of growth of the tissue. And if you slow one or other of those things down, what you should also do is affect the size of the somites. We asked the question, do we also change the size of somites, which is what we would predict? And the answer is yes. So inhibiting Wnt increases stability of NICD, which increases the period of the clock, which then increases the size of the somites. No. So we, in the context of these experiments, only work up until halfway through the gestation period, so we didn't test that. But the prediction would be that you would form bigger somites but fewer somites, because your progenitor population is going to be the same, so that's going to give rise to a certain amount of segmented tissue. If you make them bigger, then there's going to be fewer of them.